right, this is going to continue our frequency table and frequency distribution discussion. We've learned how to make a frequency table. Now we just actually have to put it together. So for the post-nature data, the first thing that we did, remember, was we found the classes. So we found that we had 16 to 24 and then 25 to 33 and so on and so forth. So we're going to put those classes over here on the left, and what we are looking at here is an actual table, right? So tables, vertical table here. Classes is in this column, frequencies are in this column. And so I can't talk and do these things at the same time, it seems. So, you know, the talk and chew bubble gum thing. And sometimes my pen just gets stuck. So here we go there, and then this is 34 here, and then this is 42 here, and then this is 43 here, and then this is 51 over here. And we discovered that there were 3 data points in this class, and there were 4 data points in that class, and there were 2 data points in the third and 1 in the last. And then we discovered that that totaled up to 10, which was the number of data points that we had, so we found them all. And there's our frequency table, or as we can also call it, a frequency distribution. So some of the key points that I want to point out here is that I want to point out that we have a title for our distribution. We have classes with the units labeled here, and then frequency over here. We have our classes labeled, so there's no overlap between one class and the other, right? We have mutually exclusive classes. So I'm going to write ME over here for that reminder, mutually exclusive classes. So each of these classes is mutually exclusive. Now something else that I want you to see is that there are no gaps here between any of these or no zeros in any of these. That's not always going to be the case. This could be a 0 or this could be a 0. The only thing that we have to be aware of is that this first one and this last one here, these two, neither of those first two, or not the first two, neither the first one nor the last one can be 0. And if they are, what that's telling us is that we have too many classes for our data. We've screwed up in some way. These can be 0. Those zeros are okay. But if the first or the last one are zeros, that's not acceptable. So those are the things that you need to realize. And if they are 0, you don't leave the class out. So if this was a 0 in the 4 place here, or the 0 here in the 2 place, you wouldn't leave the class out. You need to put that in because that's going to help us to show our shape. Now we're going to go over really quickly, and we're going to do a relative frequency histogram, and we're going to show how they're connected, and then we're going to do the cumulative frequency histogram. And once we have them all done, then I'm going to come back and I'm going to start to talk about the little bit of shape that we can start to see based upon our frequency tables and relative frequency tables, and then the cumulative frequency. All right, the relative frequency is exactly what it says it is. It's relative to something. Well, the relative to something is relative to the total number in the data set, the N, the sample size. So let's go ahead and put our classes in. The classes for a relative frequency table look exactly like the classes in a frequency histogram, or a frequency table. And so that's why I said that I focus more on a frequency table and not so much on a relative frequency table, because I figure if you can make a frequency table, you can make a relative frequency table. It just takes division to get from one to the other. So that's what I mean by my statements of I really focus on the most basic step here. So to create a relative frequency table, we're relative to the counts relative to the total. So the first one here had 3 out of 10. Or you could use one of the equivalent forms. You could use 3/10. Using decimals, what you'd want to be really careful of is that if we had a repeating non-terminating decimal, that you decide on an appropriate place for round off, so you're consistent and appropriate to what you're looking at. In this next one, we had 4/10. Now, if we were giving these as fractions, we would want it in lowest terms, so 2/5 would be our appropriate number here. Or, as a decimal, we would want 0.4. And then the next one was 2/10. And again, if we were doing it in fractions, we would want 1/5. And again, decimal form, that would be 0.2. And then finally, 1/10, or the appropriate decimal representation, 0.1. Now, the thing that you need to realize here is that whether you do it with fractions or whether you do it with decimals, the sum should be 1. With a decimal, this could be approximately 1, depending upon round off error. So it may look a little teeny tiny below or a little teeny tiny above 1, and you shouldn't freak out about that if you've done the calculations and you know that you are possibly incurring round off error. So just to check this right, 3 plus 4 plus 2 plus 1 is 10/10, 10/10 is 1, and that would be our sum for a relative frequency because of the entire thing, all right? That's what we're looking at. 0.3 plus 0.4 is 0.7 plus 0.2 is 0.9 plus 0.1 is 1, and so there's no approximate here because there's no round off error incurred, and that's a relative frequency distribution. Now the last one that we want to look at is a cumulative frequency distribution. In a cumulative frequency distribution, our classes are different. Now, this depends upon the book that you're using. In Triola's book, he uses the method of using less than, and that is totally the way that I usually do it. But I have seen books, and I use a book that uses boundaries to form cumulative frequency distributions instead. And we have yet to talk about the boundaries and the midpoints. We'll go back over those in a little while. So our classes here are going to be less than. And what we're doing is we're finding the cumulative. So we're accumulating the data as we build to higher and higher classes. So what we do is we look at these lower limits here and we say we're less than the next successive lower limit. So the first class that we have is less than 25. So we want the number of data points that are less than 25. Well, less than 25 is everything just in this class, so there's 3. And then the next one would be less than, and what do you think it would be less than? If you said less than 34, that is correct. So less than 34, and that would be 4. And then continuing on, the next one would be less than, and what do you think it would be less than? If you said 43, then you are absolutely correct. Oops, excuse me, this is not 4. We are adding these up here. So 3 plus 4. So let me just say 3 plus 4. And that's going to equal 7. So that's what we put in there. 3 and then 7 here. And less than 43, now we have the 3 plus the 4 plus the 2 in there. And so now we have 9. And then finally, we're going to have less than. And do you have any guesses here? Well, if we're staying consistent with the less than philosophy, then it would be the next level. Remember, and when we first did this, we decided that the next one would be 52, right? The next lower limit would be 52. So that's what we put in here, less than 52. So this would be 3 plus 4 plus 2 plus 1, and that will give them all. And the thing that we look at in a cumulative frequency cumulative frequency distribution, or a cumulative frequency table, is that the last number here equals n. And one of the confusing things after looking at just a frequency distribution or a relative frequency distribution is the fact that here we're actually looking at these we're actually looking at the counts. So we're adding up the data, and we add up to the 10 here. So this one is the total number afterward. So this 10, of course, is going to show us the total number. So we have 3, and then we have 7 of the 10, and then we have the 9 of the 10, and then we have the 10 of the 10. So these numbers are larger than the data in any one. It's the fact that we're less than a certain number here. So let's go and talk about what kind of shape that we can see, what distribution we can see. So one of the things that we can see as we look at this frequency distribution of purse snatchers is that 3 and 4, those are fairly large amounts of our 10 here, right? And so we have 3, 4, and then only 2 and 1. So most of our purse snatchers, if you think about it in that way, most of our purse snatchers are right in this range here. And then there's, to a lesser extent, in this higher range here. So just looking at the data when it's summarized in this particular way, described in this particular way, remember we're doing descriptive statistics, the purse snatchers tend to be young. Well, duh, purse snatching is kind of a crime of opportunity, right? You snatch somebody's purse and you run away as fast as you can. Do you think the old guy or the old gal is going to be snatching somebody's purse and running away? As much as the younger person who can probably run like the dickens. So I think that that's very telling of what we would expect to see. Now, when we go to the relative frequency distribution, another way of looking at this is in percentages, right? So 30% of all purse snatchers are very young, 16 to 24, and 40% of them are between 25 and 33. Got to get a little bit braver, right? Not only do you have to have the younger age, but you got to be braver too. 25 to 33-year-olds, they're a little bit more maybe mature, confident, I don't know, whatever you want to say. Only 20% are 34 to 42 years old, and only 10% are in the upper ages. And so by taking it into decimals or percentages, you are starting to make a comparative. So that's where the relative frequency adds to what you're seeing with just the numbers. And then finally, with our cumulative, is that we're seeing that most crimes, by the time we get to 34 years old, anybody less than 34 years old, 7 out of the 10 that are total here are going to be committing the crimes. So you can start to see where does the majority of the data stack up. What I take away from this cumulative frequency distribution is that purse snatchers are young. All right, now the only thing that I have yet to talk about are boundaries and midpoints. So let's go ahead and talk about boundaries, because remember I did mention that some books will use boundaries down here, so it's a perfect segue into that. So boundaries are gutters. They're what's partway between this class and this class, so that we can make them touch but not have any data points actually falling in between. So what we want is from here to here, we want the midpoint. And that can be found in two different ways. You can take the two numbers and you can add them together, and then you can divide by 2. That's how you find a middle, right? And then you get that this is 24.5. And you can do that for each of these. 34 plus 33, and then divide by 2, 33 and a half. 42 plus 43 divided by 2 is 42 and a half. That would be one way, and 51, 52 here. The only problem with that method is that that leaves us lacking here. So my preferred method is to instead do this, and I'm going to run out of time, so I'm going to have to do this more in the next video. I instead take the larger one and subtract the smaller one. And you'll see in the next video what I'm going to do with this. 0.5 is what I'm going to get out of it.